All right, let's use the nano spec. So first thing we need to do is turn on the monitor. It should beep. And then I like to wait a little bit for the cursor to light up. Then we turn on the brain. And there's a metal switch back here. It's in the tutorial. So, enable data link. No. Wavelength 480. Oh, it is. Yes. If it wasn't, you put in the number that it is until it works. And index of refraction option? No. Enable printer? No. Okay. Focus on reference with 5x objective and set the gain. This wafer just happens to be a patterned wafer that you can use the nanospec to peer into small features. It just happened to be there. But this is our reference wafer. But we're not using the thickness of the oxide as a reference. And here it's green, so it's about 9,000 angstroms. Reference really means like ground, measuring with respect to ground. So this is supposed to be 0 angstroms, although by being in air it's about 20, 25. So you just place it on there and then find a spot where you're not on the oxide, and then this is the 5x objective and you just twist it and it clicks nicely into place. Now this is part of the calibration. We need to set the intensity to, and it tells you right there, 65 to 67. There's a knob right here. A little sensitive. Okay. Again, between 65 and 67. Okay, so there we go. So I'm there. I have to make sure that it's focused. And it's really hard to film that, but there's a hexagon in there, and when the hexagon is sharp, it's focused. And so then you press enter to continue. And now this, basically it's a Fabry Perot device that's moving a width of a chamber, right, getting the wavelength. So now it's all set to go, and today we're just going to measure flat films, non-pattern films, so we can keep it on the 5x and go from there. So what program do we want? It does help to know what you're measuring. So there's a wafer over there that's orange, that's roughly 2,300 angstroms. The reference wafer is green, that's about 9,000. There's something brown that is about 450 angstroms. So you kind of have to tell it ahead of time what you're looking for. Recipe number 1 is what we're looking for. Okay? Because that's thick oxide. All right, what objective? I've got it on the 5, so I enter in 0. All right, focus on the silicon reference. I'd already done that. Now I'm going to press measure. And now it's calculating what 0 should be versus wavelength. Okay. Enter sample ID. Doesn't really matter for this exercise. 1, enter. All right, so now you want to move it to where there's oxide, and you look under the lens and you push it around until you can see what you're doing. Although there's a white light that can pick up the dust, and then you can move it by eye until you get what you want. And now that I'm looking at it, I can see that it's green, I can see that it's focused. There's some better pictures in the manual. And you just press measure. Okay. 9,655 angstroms. Now, yeah, what is the repeatability of this measurement? Well, we can just take a few, right? Right? So you can find the mean and take the standard deviation. Right? So that's the calibration wafer. That's what you should get. Then we place that away. This isn't really being processed, so we can use our fingers. And you place it face down into the wafer holder and just twist it. And yeah, that's a standard. It's supposed to be 9,617 plus or minus 3 angstroms. That was probably used an ellipsometer to do that. All right, let's try another wafer. Okay. This one's got a different color, so we'll have a different thickness. Put it in the center. Now, if it's a different thickness, I might have to refocus it. All right. So I will. Okay. So let's just take 5 measurements. Okay, so you can see that it's different. It's got a different mean and different standard deviation. All right, so that's great. Now, one could measure it across the wafer and get a thickness map of the whole thing. And there's systems that do that automatically. Now this wafer's been beat up a little bit, but it should be about 450 angstroms. It's slightly tan. I'm just going to double check that it's focused. It is. Let's try it again. You can see that it's jumping around a little bit more, and that's because it's harder to measure thinner thicknesses, because you need you're going for the wavelength of light. It's dependent on the thickness, and so the thinner you are, the shorter the wavelength you need to get a good measurement. So other systems have a UV to extend the range, but also this is also guessing thick. We have another recipe that assumes thin oxide, and that guesses thin. But regardless, it's pretty good. Maybe I'm just misremembering that it's that it's a little bit thinner than I thought. Okay, so those are things that work. Just like with the 4-point probe, let's get something that doesn't work. So this is aluminum, and the properties with light are much different. And so it really shouldn't be able to measure aluminum. Out of range, right? It just can't do it. So, gee, if there was only a way to measure that thickness. How about we use the 4-point probe to measure the resistivity, and that correlates with thickness. There you go. It all lines up. That's it for this station.